The first example of application of the Boltzmann formula is concerned with the quantification of the amount of disorder associated with the different conformational states of biological molecules, such as proteins, sugars, DNA, and so on. Let us consider a protein molecule containing 100 amino acid residues linked end-to-end and assume that each amino acid can adopt 3 different conformations of identical energies. The question we ask here is, what is the fraction of the entropy that is associated with the multitude of conformational states of this protein? To answer this question, we first need to estimate the number of microstates of the system, W. That is the number of conformations of the protein. There are 3 choices for the first amino acid in the sequence, 3 for the second amino acid, 3 for the third, 3 for the fourth, and so on. Since there are 100 amino acid residues in a protein, to find the number of protein conformations, we multiply 3 by 3 by 3 and so on, a total of 100 times, and obtain W equal 3 to the power 100. In general, a molecule made of N residues, each able to exhibit C states, will have a number of conformations equal to C to the power N. In our example, W is equal to 3 to the power 100, which is approximately equal to 5 times 10 to the power 47 in scientific notation. A mighty large number. Recall that Avogadro's number is only 6 times 10 to the power 23. So, according to the Boltzmann formula, the contribution to S arising from the conformational disorder of one protein molecule is S equals k log of W, and W is 5 times 10 to the power 47. So, S per molecule is equal to 1.381 times 10 to the power minus 23 times the natural logarithm of 5 times 10 to the power 47, which is equal to 1.5 times 10 to the power minus 21 joule per Kelvin per molecule. The entropy per mole of protein molecules is given by S sub m is equal to S per molecule times Avogadro's number, since entropy is an extensive function. S sub m is equal to 1.5 times 10 to the minus 21 joules per Kelvin per molecule times 6.022 times 10 to the power 23 molecules per mole. So we get S sub m equals 913 joule per Kelvin per mole. If we compare this entropy to the entropy of small molecules, we see that the conformational entropy of large molecules is indeed very large. These calculations also tell us that during protein folding and denaturation, we should expect very large changes in entropy. Indeed, in the folded state, a number of amino acids participate in alpha helix or beta sheet structures and are not free to adopt any conformations they want. Hence, in the folded state, the protein entropy is expected to be much smaller than in the denatured state. A second application of the Boltzmann formula is concerned with the concept of residual entropy. The situation where the entropy of a crystalline system does not approach zero as the temperature of 0 Kelvin is approached. The observation that the molar entropy of some pure substances does not reach zero as 0 Kelvin is approached is not actually a proof that the third law of thermodynamics is not valid. Indeed, in some crystalline systems, there are no energy advantages for the system to adopt one configuration over another. In such situations, the crystal system may adopt different configurations. to illustrate the residual entropy concept, that is the fact that the entropy of a substance may not be zero at 0 Kelvin, we will consider two examples. The first example considers the case of carbon monoxide or CO crystals. The carbon and oxygen atoms have slight differences in electronegativity and size, so the CO molecule is slightly polar. That is to say, CO exhibits a small dipole moment. When polar molecules crystallize, the energy of the crystal is lowest, that is, the crystal is in the most stable state, when the molecules are organized as shown on the cartoon. In this cartoon of a perfect CO crystals, CO molecules point in the same directions when in the same row, and alternate neighboring rows have CO molecules pointing in opposite directions. Such a crystal is perfectly ordered and should exhibit a zero molar entropy at 0 Kelvin. In actuality, carbon monoxide crystals remain imperfect when examined near 0 Kelvin. The defects in the crystals consist in CO molecules pointing in the wrong direction, as evidenced, for instance, for the molecules in the blue circle. Such a situation can arise as a result of a cooling process that was too fast, and while the molecule of interest may have slightly preferred to be in the other orientation, it actually did not have time to reorient itself during crystallization. Another possibility, less commonly observed, is that the two molecular orientations correspond to the same energy, in which case the molecule does not have any preference as to its orientation during crystallization. In the case of CO crystals, assuming that the two orientations of each CO molecule correspond to the same energy, would lead to a number of microstates equal to 2 to the power n, where n is the number of CO molecules in the crystals. If we take n to be Avogadro's number, then the molar entropy at 0 Kelvin should be equal to S sub m equals to k times the natural logarithm of 2 to the power n Avogadro, equal to k times n Avogadro times log of 2. Since Avogadro times the Boltzmann constant k is equal to the gas constant R, we obtain the molar residual entropy of CO crystals at 0 Kelvin is equal to R times the natural logarithm of 2. A similar situation is encountered during the crystallization of water, where, as a result of the different relative orientation of the H2O molecules in the crystals and the formation of different hydrogen bonds, there are 3/2 to the power n microstates. So at 0 Kelvin, the molar residual entropy is calculated to be S is equal to R times the natural logarithm of 3/2, in agreement with experimental measurements.